I'm going to start recording the session. Who is presenting today? We had 2 presentations last week. One didn't go through, so let me check. Matt, you're here, Matt?
Yeah.
So you're presenting chapter 8, yeah?
Yep. Let me
So,
just get up.
No, just bear with me. I'll let you know when.
Okay.
Just so we have gone through ping traceroute. We have gone through ICMP. We have gone through ICMP version 4 and version 6. I told you that both versions, they do connectivity tests to make sure that the host, the destination host is present. We can confirm it if it exists. I also told you the story behind traceroute, which gives us the hops that a packet is taking to get to the destination. So the difference between ping and traceroute, ping just tests the reachability, whereas traceroute or traceroute or tracer, depending on the operating system that you're using, also tells you the hops that you are traversing to get to the destination. ICMP version 4 and version 6, they do both do the connectivity test for you. However, ICMP version 6 has a couple of new messages that those new messages are used as part of a protocol for neighbor discovery, we call it. So 2 messages, router solicitation message and router advertisement message, if you remember RSRA, are used as part of what we know as a SLAC, stateless address auto configuration. So in order to assign IPv6 addresses for devices without having a DHCP version 6 sitting there, we can have some scenarios whereby DHCP version 6 is also available and we still use these messages. But if you don't have a DHCP server, you are an IPv6 enabled device, you come up, you need to get an IPv6 address, then the router is going to send you RA message and then tells you that this is the prefix, IPv6 prefix that you have been assigned, pick up an address from there. Or if you come up late, if you boot up late and you don't have such info, then you can send a router solicitation message to the router asking for RA message to be sent to you so that you can have the chance to get to know your prefix, your default gateway, your DNS server address, etc., etc. We also had 2 other messages introduced by ICMP version 6, whereby ARP in IPv4 was now taken care of by ICMP version 6. Those 2 new messages are neighbor solicitation, NS, and neighbor advertisement. So you know what ARP, address resolution protocol, does. So basically, if you know the destination IP address through, let's say, DNS, but you don't know the associated destination MAC address, then you need to use ARP process to find out the binding. We don't have ARP as such in IPv6. Instead, nodes, IPv6 enabled nodes are going to send a neighbor solicitation message asking who has this IPv6 address. Come back to me with your associated MAC address. And then neighbor advertisement, NA message is going to come back in response to NS, telling you that this is me with this IPv6 address, and here you are, this is my associated MAC address. So chapter 7 almost covered last week. Just one point which was important before we move on to chapter 8 is to do with traceroute. So remember, we have TTL field in IP header, time to live. The main idea behind TTL was that to not allow an IP packet to travel across the network endlessly. And therefore, we wanted to set a time span or a lifespan for which that IP packet is alive. We set TTL to 255 at the source or sender, and then at each hop, the TTL is going to get decremented by 1. Therefore, we don't allow an IP packet to go beyond 255 hops away. You know also that ICMP is going to be encapsulated within an IP packet. So if you remember from this slide that we had it previously, IP header, 20 bytes, and then inside the payload, you're going to have ICMP header as well as ICMP payload. Now, the idea with traceroute or tracer is that we're going to make use of that TTL field. How? Instead of setting that TTL field into 255 at the sender or source, we're going to set it to 1. And then we send an ICMP packet with TTL1. TTL1, it simply means that that packet is going to travel only 1 hop away, yeah? Because then 1 becomes 0, decremented by 1, and then it's going to be discarded. This is exactly what TTL wants. TTL wants it for that TTL value 1 to be decremented to 0, and then as a result of that, a time exceeded notification being generated by that first hop sent back to the sender. In that way, the sender gets the chance to know who is the first hop. And then traceroute does the same again, but this time with TTL2. So we send an ICMP packet to 2 hops away. And then at the second hop, that TTL value is going to decrement it by 1, but it was previously decremented by 1 in the first hop, so it becomes 0. Another time exceeded message is going to be generated now with the second hop. And in this way, sender gets to know who is the sender of that time exceeded message, so who is the second hop, and so on and so forth. So this is how, unlike ping, traceroute, or tracert comes to know which hops that IP packet is traveling through. So just wanted to mention this one, and I think the rest was covered during that lecture. So let's move on to next chapter.
So should I start presenting?
Yes and no, just bear with me, please.
Okay.
Yes, go on, Matt, put your slide on.
Okay. So address resolution protocol. The contents we'll be looking. Oh,
just bear with me 1 sec, please.
go.
Did you share it on Teams, yeah?
Yeah, I have.
Okay, go on, man.
So address resolution protocol, the contents that we'll be looking today will be MAC and IP, as well as obviously address resolution protocol, and then the issues with ARP. So ARP overview. Every device on the Ethernet network has a unique Ethernet MAC address. When a device sends an Ethernet layer 2 frame, it contains the following: a destination MAC address and a source MAC address. The destination MAC address is the destination device on the same local network segment. If the destination host is on another network, then the destination address in the frame will be that of the default gateway. The
MAC
source MAC
address
address
itself is 48-bit length, if you remember. And then it's also called a BIA, burnt-in address. So it's an address that comes directly with your network interface card. NIC, NIC, being a NIC on your phone, your iPad, your PC, your tablet, they all have MAC address. And manufacturers who generate these MAC addresses, who generate these network interface cards, they make sure that these NIC address, BIA or MAC address associated with that NIC, is unique. Yeah, physically unique. Regardless of where you take that device to, that data link layer, MAC address, NIC address, or BIA address, whichever term you want to use, is going to be unique and associated to that single network interface card only. Move on.
So source MAC address is the MAC address of the Ethernet NIC on the source host. Moving on to ARP overview, well, continuation of ARP overview. To send a packet to another host on the same local IPv4 network, a host must know the IPv4 address and the MAC address of the destination device. Device destination IPv4 addresses are either known or resolved by the device name. However, MAC addresses must be discovered. A device.
So just to recap, in order to send some data from point A to point B, 6 pieces of information are required with regards to addressing. So we need source and destination port number. We need source and destination IP address. We need source and destination MAC addresses, depending on the layer and depending on the encapsulation level that we are in. Yeah. So go on.
A device uses address resolution protocol, also known as ARP, to determine the destination MAC address of a local device when it knows its IPv4 address. ARP provides 2 basic functions, such as resolving IPv4 addresses to MAC addresses, as well as maintaining a table of IPv4 to MAC addresses mappings.
So the destination IP address comes from DNS. Yeah, you say www.wahidhaidari.com. There is a DNS there that translates this to your destination IP address. It's 1.1.1.1, for instance. So we know about destination IP. We also know about our own IP. It's been either statically assigned or through DHCP. We also know about our source MAC address, because that's a physical address, unlike IP, which is a logical address. It is MAC address, source MAC address is the physical address associated to my own network interface card. So with regards to layer 2 and layer 3 addressing, 3 out of 4 pieces of information is known. The only missing part is destination MAC address. We don't know the destination network interface card's physical address associated to that. And this is the job of ARP, Address Resolution Protocol, ARP, to find out what that associated destination MAC address to destination IP address is. For this, any device, including the pieces in front of you, they have a table called ARP table. So everyone please open up CMD on Windows and then just type ARP-A. This is the MAC to IP binding table on your local machine, meaning that at the moment, this PC in front of you is aware of these IPs being bound to these MAC addresses. This is not set in stone, as they say. So every now and then they new devices will be added, some old devices will be removed, etc., etc. Therefore, there is always a lifespan attached to these entries, and then the ARP table sometimes gets flushed, and then new entries will be added, or we update them. Yeah, this is your PC, but back to your packet tracer activities, or here in the lab, if you do the real equipment, you're going to exactly have the same tables on switches, on routers, on any device when it comes to data communication. Yeah, move on.
Moving on to ARP functions. When a packet is sent to the data link layer to be encapsulated into an Ethernet frame, the device refers to a table in its memory to find the MAC address that is mapped to the IPv4 address. This table is stored temporarily in RAM memory and called ARP table or ARP cache. The sending device will search its ARP table for a destination IPv4 address and a corresponding MAC address. If the packet's destination IPv4 address is on the same network as the source IPv address, the device will search the ARP table for the destination IPv4 address. If the destination IPv4 address is on a different network than the source IPv4 address, the device will search the ARP table for the address of the default gateway. Each entry or row of the ARP table binds an IPv4 address with a MAC address. This means that you can locate an IPv4 address in the table and discover the corresponding MAC address. The ARP table temporarily saves the mapping for the devices on the LAN. If the device locates the address, its corresponding MAC address is used as the destination MAC address in the frame. If there is no entry found, then the device sends an ARP request.
So ARP request is going to be a broadcast frame. Everyone is going to receive it. Basically, the guy is sending this. Whoever has this IP address, please come back to me with your MAC address. But because we don't know who has that IP address, we're going to send this in the broadcast form so that everyone can receive it. But what about the ARP response to this ARP query? That is going to be a unicast because only one guy is associated with that destination IP address, for which we are after the associated MAC address. So he comes back to you and say, hi, this is me having the IP 1.1.1.1, and this is my MAC address. Yeah. As we go on, remember, in IPv6, we have exactly the same story. The difference is that there we don't have broadcasts, instead we have multicasts. There we don't have ARP, instead we are having ICMP version 6, neighbor solicitation and neighbor advertisement, NS and NA messages. Yeah, move on.
Moving on to ARP request. An ARP request is sent when a device needs to determine the MAC address that is associated with an IPv4 address, and it does not have an entry for the IPv4 address in its ARP table. ARP messages are encapsulated directly within an Ethernet frame. There is no IPv4 header. ARP requests are broadcasts. They are flooded out of all ports by the switch except the receiving port. All Ethernet NICs on the LAN process broadcast and must deliver the ARP request to its operating system for processing. Every device must...
Just before we move on, everyone please open up NetAcad in front of you as well. Go to section 8.1.2. Chapter 8.1.2. So you should be seeing this diagram in front of you on NetAcad there. Yeah. The important thing here is the color. The color. So from left to right, this PC to that server, when they want to communicate, the IP does not change at all, because IP is a logical addressing mechanism, and it's also known to be an end-to-end form of addressing. So as we go through 2 hops here, let's imagine we go through 2 million hops, still IP does not change. Don't be late. Don't be late. However, the MAC address keeps changing at each network segment. Yeah, look at the gray part, and then you look at this violet color. And then if you have other hops in between also, NIC keeps being stripped off and added as you travel from one network segment to another, depending on the data link layer topology and technology that you have at each new segment. And if you think about it, it makes sense because NIC is a physical way of addressing associated to the port and network interface card behind that port. And therefore, as we expect, it changes from one hop to another. Move on, Matt.
Every device must process the ARP request to see if the target IPv4 address matches its own. A router will not forward broadcast out of other interfaces. Only one device in the LAN will have an IPv4 address that matches the target IPv4 address in the ARP request. All other devices will not reply. Moving on to ARP reply. Only device with the target IPv4 address associated with the ARP request will respond with an ARP reply.
i.e. unicast. Yeah? One.
Only the device that originally sent ARP request will receive the unicast ARP reply. After the ARP reply is received, the device will add the IPv4 address and the corresponding MAC address to its ARP table. Packets destined for that IPv4 address can now be encapsulated into frames using its corresponding MAC address. If no device responds to the ARP request, the packet is dropped because the frame cannot be created. And entries in the ARP table are timestamped. If the device does not receive a frame from a particular device before the timestamp expires, the entry for this device is removed from the ARP table.
If you think about it, without timestamps, if you just send ARP queries and waiting limitlessly for someone to come back to you, again, that makes you prone to some cybersecurity attacks, isn't it? Because then the attacker can basically keep you waiting. Yeah? And then saturate your resources as such. Move on.
Moving on to ARP role in remote communication. When a device IPv4 address is not on the same network as the source IPv4 address, the source device needs to send the frame to its default gateway. This is the interface to the local router. Whenever a source device has a packet with an IPv4 address on another network, it will encapsulate that packet in a frame using the destination MAC address of the router.
So we always have two different scenarios with these things as we go on. When we want to communicate inside our LAN, or when we want to send something to the remote network over the internet. With ARP, we still have the same two scenarios. If the person you want to contact is someone who is sitting in the local area network as you are sitting, therefore both of you are on the same network or subnet, then ARP is taking place exactly as Matt described now. If the guy is sitting somewhere beyond your LAN, therefore you need a taxi to get to the remote network, to the internet. And that taxi is your default gateway. Once again, default gateway is the closest router interface towards your LAN. And then the job of ARP, Address Resolution Protocol, is to find out what is the MAC address for that default gateway, for that router interface. And then exactly the scenario that you see on the screen here happens, yeah? So here, the destination IP address is on the remote network, on a remote network. And therefore, to be able to get to there, you need to go through default gateway. And therefore, ARP's job is to find out this MAC address, 000C, for those of you who have NetAcad in front of you. Yeah, so ARP needs to find 000C. Of course, for the sake of brevity, they have put only 4 characters of the MAC address. Yeah, so it's going to be 48 bits. And in hexadecimal, it's going to be 12 characters or 12 digits, not just 4. But for the sake of brevity, they have put just 000C. So ARP now needs to find out that MAC address because your destination is on a remote network, not on a local network. How to find out, by the way, whether your destination is someone on your LAN or someone on a remote network. How do we know whether we need to go and find destination MAC address for the default gateway or destination MAC address for someone who is sitting next to us on this LAN? Anyone?
Doesn't the router keep the table of all MAC addresses, I believe?
No.
Oh.
Could you ask
Just-
again, please?
Just you yourself, let's say you are PCA in this scenario. How do you know whether the destination IP is someone sitting next to you or someone on a remote network? Anyone? Your network address and your subnet mask. Subnet mask is telling you how many bits from left to right constitutes your network address, isn't it? If source and destination are both on the same network, on the same subnet, therefore, the network address of both IPs must match. Because if you remember, I told you that network address plus subnet mask is like surname. Yeah? My surname is Haydari. Yeah? So whoever is in my family, i.e. whoever is in my LAN, is going to share the same surname with me. My siblings are going to share the same surname with me. Therefore, if I'm talking to someone who is within the family, their surname should be Haydari as well, isn't it? Whereas if your destination IP combined with the destination IP subnet mask for the destination network is telling me that you are talking to someone else, then we are on different networks. Therefore, we need to contact default gateway to reach him. Does that make sense? Move on.
The IPv4 address of the default gateway is stored in the IPv4 configuration of the host. When a host creates a packet for a destination, it compares the destination IPv4 address and its own IPv4 address to determine if the two IPv4 addresses are located on the same layer 3 network.
Read that sentence again.
When a host creates a packet for a destination, it compares the destination IPv4 address and its own IPv4 address to determine if the two addresses are located on the same layer 3 network.
Two different surnames or two similar surnames, yeah? Go on.
If the destination host is not on its same net, let me start that again. If the destination host is not on its same network, the source checks its ARP table for an entry with the IPv4 address of the default gateway. If there is not an entry, it uses the ARP process to determine a MAC address of the default gateway. Moving on to remove entries from an ARP table. For each device, an ARP cache timer removes ARP entries that have not been used for a specified period of time. The times differ depending on the operating system of the device. For example, newer Windows operating systems store ARP table entries between 15 and 45 seconds.
Just go back to the previous slide. Everyone pay attention to the topology that you see in front of you. The way that ARP works is that if PCA wants to send information, data to PCC and doesn't know the associated MAC address of PCC's IP address, will send ARP request and PCC will come back with ARP reply saying that this is my MAC address. Now, can anyone tell me any possible attack scenario here? Because from the video I showed you last week or the week before, I can't remember, I told you how attackers think. Yeah, they first learn how a protocol works, and then they start thinking about how to mess up with the process. I know that you know the answer. No surprise to me. Keep it up. So from PCA to PCC, we want to send data, and this is how ARP works. Yeah, I send a broadcast ARP query saying that whoever has this IP address. Please come back to me with your MAC address. Now, how do we mess up with these settings? Adi,
Can we do a spoofing attack or man in the
Like-
middle?
explain the attack. Don't give me the
So
name.
okay, we could so I'm assuming PCA. Okay, so what the attacker can do is get in between PCA and PCC. So before the request goes back to PCA, it
Before the
intercepts that
response
the response goes back
goes
to
back,
PCA.
good, good, good. So if PCB jumps in before PCC's response, claiming that I am PCC's IP, and here you are, this is my MAC address, then he can potentially become, yes, of course, man in the middle attack, but not always man in the middle attack, depending on how he wants to mess up with what he receives. But he can basically receive the communication that was supposed originally to go to PCC. You see, a very simple cybersecurity attack. But if it was me, I would have jumped in to claim that I am the default gateway, not PCC. Yeah, and not only to PCA, to whoever I can. And therefore, any remote traffic destined for the internet, for instance, can be in my hand. Yeah. Move on, Matt. We have a section at the end of this chapter. We get to that as well. Go on. And a
Moving
bit
on.
quicker. You're muted.
Hello? All right.
Go on.
Moving on to ARP tables on networking devices. On a Cisco router, the show IP ARP command is used to display the ARP table as shown in the figure. On a
So
Windows,
similar to ARP-8 on your PCs. So this is the iOS packet tracer or real devices command that you need to issue. I told you any device that you are facing is going to have ARP table somewhere. Yeah, go on.
on a Windows 10 PC, the ARP-A command is used to display the ARP table as shown in the figure on the right.
Good. Move on.
ARP issues, ARP broadcast, and ARP spoofing. As a broadcast frame, an ARP request is received and processed by every device on the local network. These broadcasts would have minimal impact on the network performance. However, if a large number of devices were to be powered up and all start accessing the network services at the same time, there could be some reduction in performance for a short period of time. After devices,
Everyone comes up. Everyone wants to send and receive some data. They're going to send broadcast ARP queries. Broadcast, saturating the network. So at the beginning, if this is the case, at time 0, all coming up, you're going to have a degradation in your performance of the network because it's been saturated by broadcast messages. Remember, guys, broadcast is something that you see in many, many protocols as the default behavior. I told you this story before. Broadcast was the very first thing that every protocol designer thought of when they designed a protocol. Because all these protocols, switching protocols, routing protocols, security protocols, at the end of the day, yeah, they are not working in isolation. They are communicating with each other. And the simplest form of communication is when you are after some particular piece of information, but you don't know who has that particular piece of information. You send a broadcast asking whoever has this piece of information, come back to me. It's not just ARP, as I said, many protocols. And it's not just when you are after particular piece of information. Even with routing protocols, sometimes you want to share your knowledge with others. You have OSPF, a link state routing protocol, whereby you want to share all the subnets that you're aware of with your neighboring OSPF routers. You send it. In broadcast form, you're telling everyone, this is my view over the network. This was the design of many protocols. However, as we moved on, as we got matured, we came to know that this is not the best way because we are also saturating our bandwidth sometimes unnecessarily. Yeah, and that's why with IPv6 you see that we don't have broadcast. We know that multicast is going to be more efficient, so we moved on to multicast instead of broadcast. Floods, broadcast floods are the issues with ARP. Move on, Matt.
After devices send out the initial ARP broadcast and have learned the necessary MAC addresses, any impact on the network will be minimized.
This was the attack that I was talking about. Go on.
The use of ARP can lead to a potential security risk. A threat actor can use ARP spoofing to perform an ARP poisoning attack. This is a technique used by a threat actor to reply to an ARP request for an IPv4 address that belongs to another device, such as the default gateway, as shown in the figure.
ARP poisoning attack. Yeah. Go on.
The threat actor sends out an ARP reply with its own MAC address. The receiver of the ARP reply will add the wrong MAC address to his ARP table and send these packets to the threat actor. And that is the end. Any questions?
Move on, Adi. So very good, Matt. But a couple of points. Always have introduction and summary slide. Try to not read out from your notes. I know that you try to be accurate, which is good, but I'm just saying that for the sake of official presentations, if you have, which you have, by the way. Move on. Adi, what was the question?
So a quick one regarding the ARP attack. In what scenario? Because I'm guessing it's not the same as. All right, so let's say we're trying to establish a connection with a server, maybe via Telnet or SSH. If Telnet is used, I'm guessing one can use Wireshark to sort of try to see what traffic has been sent. Would that be an example of how one can sort of intercept the data or see what's going on between the hosts to whatever sending information to, if my question makes sense?
So I'm not sure if your question is related to ARP or not, but I assume not. So yes, if you're using Telnet, then all the communication is going to be sent and received in plain text. And therefore, if an attacker sits in between using Wireshark or any eavesdropping tool, as we call it, then they can see all the communication in clear text. Even your username is going to be sent and received in plain text, all your communication with Telnet. And that's why Telnet is forbidden, and we moved on to SSH, with which we encrypt all the communication, username, password, everything. Make sense?
Okay, thank you. So in that case, what would be real life, like real world scenario of an ARP attack?
This is exactly, go back to the previous slide.
No.
This is ARP poisoning is a real scenario of ARP attack.
And also, how do I explain it? Like an example.
Yeah.
You're like okay, so
So you're going to send a packet to Matt. I'm sitting in between, and I'm telling you that if you want to send that packet, I am that IP or MAC address owner. Send it to me. I am Mac. I am impersonating Matt. Did I say Mac? I am impersonating Matt's identity, and you are going to send that traffic to me because you believe that the MAC address, the destination MAC address is Matt, which is not. It's me. So I am now in possession of your data,
okay,
which you were supposed to send to Matt. Make sense?
yeah,
Good.
great. So when we
move on.
I am so sorry.
No,
when
go
you
on.
talk about packets, we're talking about what sort of packets, or it can be any data. I don't know. I'm trying to get like
When we are talking about ARP, we are talking about the context of layer 2 and layer 3 of OSI. That disregards completely what comes in the payload of higher layers. We don't care what is inside your application layer, be it email, be it internet chat messages, being whatever. ARP does not care, is not aware. ARP only takes care of layer 2 addressing to layer 3 addressing bindings. That's it, regardless of the type of the payload or type of the data that that IP packet is carrying. Yeah, remember the focus here is on the headers and the information which is inside fields within these headers. One information or one piece of information being destination MAC address, one piece of information being destination IP. And all ARP does is the binding between these two. They don't care what is inside the payload. Yeah? Adi, happy?
Yep, good, thank you.
So the first 8 chapters finished. What I want you to show me now is to open up NetACAD, go to the assessment page and show me how many exams have you done and show me the marks for those exams that you have done. So, how many chapters? Shoot me. Bring up the marks page. Team, 62% each chapter is it? First 2, okay. What about the, hold on. 3, 2, was it, hold on. Was it closed book, I assume? Was it closed book?
What does that mean?
When you did the tests, you didn't look at the materials. You did it closed book.
Yeah, close book.
Great. So please do it again. Again, closed book. Aim for 75% plus, guys, closed book. If you're after certification. Yeah, which you should. Yeah. So you are a cybersecurity student, not computer science. The ideal job for you, all of you, apart from being cool and enjoying your critical age, is to land in a SOC center, yeah, security operations center, as a cybersecurity analyst. And this is just like high school degree if you think about that job. Yeah, so it's that easy, but that important and that basic. Yeah, so aim for 75% plus for the certification. Thank you, team. Good. How many chapters? Please, by next week. How many chapters? Can I see the marks? Well done. Great. Was it close with? Yeah, okay, that's good. Second time, do it close with, yeah? Well done, that's great. How many chapters? Please, Alexei. Sorry, Maxim, don't disappoint me. How many chapters? You haven't done? That's the exam, yeah? No, you haven't done it. Oh, yeah, you've done 80%. Well done. Go back there. Have you done the second two as well? That's great. How much was it? That one? That's great. Now you're speaking. I like that. So, guys, I'm not going to check every one of you. but I'm going to check every one of you by next week. Today, I'm going to quickly finish chapter 9 and chapter 10. And that gives you access to, I think, 3 group exams, yeah? The first 2 chapters is one bundle. The second 2 chapters is another bundle exam. And then the next 5 chapters, yeah? Thorn, how many chapters? Nothing?
Yeah, nothing.
By next week, I want everything, yeah? Luca, how many chapters have you done? These by next week, yeah? I want 3, I think, team, is it 3 bundle exam till end of chapter 10, yeah? So I want all 3 by next week, Luca. How many chapters? 3 bundle exam by next week. Adi, how many chapters? 2 bundle exams, you mean, or 2 chapters? 1 bundle exam. So 3. Good. How much did you get on that one? Was it close with? That's good. How many? Next week, 3. Yeah. So this is formative assessment of this module, guys. Yeah. So NetAcad is going to give you feedback on things that you are not following. About labs, I believe that I asked you to cover all the chapters we have done so far and come back to me with question. Except one person who asked me some interesting question. I haven't had any questions from you, which means I assume everyone is doing it great and okay and no issues. If not, soon you will be failing this module. So please start getting engaged. We are almost half of the first semester. Yeah. So transport layer. Transport layer, you have seen it previously in networking module as well. So that's why I am going to be quick on these 2 chapters, because they are pretty much a recap of the module that you have done last year with me. So how it enables network communication in a sense that how are we going to establish sessions with TCP, or how are we going to take care of reliability of communication, again, thanks to TCP, or how are we going to ignore reliability, but care more about the speed, thanks to UDP, yeah? This is what this chapter is going to talk about. So in TCP/IP protocol set, you're going to see transport layer, of course, sitting from bottom to top at layer 3. Transport layer is associated with different applications that are running on these 2 machines. One machine on the left, one machine on the right. These 2 machines, at the same time that they are attending a video conference, the guy is naughty and he's also sending some emails. And at the same time, he has some VoIP calls. And at the same time, he's chatting with Salvatore. So all these applications are running at the same time. So far, we have said that thanks to layer 2 and layer 3 addressing mechanisms, these 2 machines can find each other, can locate each other, and can get to each other. So from communication viewpoint, from point A to point B, we can get to that point. But once we get to point B from point A, what is the correct application on which I need to deliver this data? Yeah, because I can't deliver the data that is destined for VoIP, voice over IP, to chatting message application or messaging application, or I can't deliver it to email client software. Yeah. So how can I distinguish between these applications? A couple of things to do with responsibilities of transport layer. Transport layer is going to manage what we know as a conversation. Conversation is going to be one set of data flowing between a source app and a destination app. That one flow for chat, for instance, that one flow for VoIP, which is a separate flow, by the way. How these can be tracked individually and separately. This is what transport layer is going to do for us. Another thing that transport does, from now on, I refer to transport as layer 4. And of course, you know that I am talking in the context of OSI, not TCP/IP, because in TCP/IP it's layer 3 from bottom to top. But as I said, we always use OSI as the main reference model. Yeah. So layer 4, in particular TCP, is also responsible for segmenting data and then reassembling data at the destination site. So segmenting at source, reassembling at destination. Why? Imagine that I've got a very large chunk of data. Want to send it from point A to point B. I can't just deliver it at one go. Yeah, because I don't have the full control over the path. Even if I have, and even if I want to do this, I can't do this reliably. Imagine that I have 1 terabyte and I send everything at one go. The very, very last byte is going to face some difficulties and therefore is not delivered. That simply means that I need to resend the whole thing again, which is again something not reasonable. Therefore, I need to segment that data. This is what layer 4 does. And then at the destination side, before that chunk of data being processed in order to be delivered to the application layer, which is the layer above, I need to reassemble the whole thing again and provide or resemble a full picture before delivering it back to the application layer on the destination side. This is again what transport layer does. So we said transport layer does this, transport layer does that, but how? Again, header. We're going to add a header. And this process, as you know, is called encapsulation. You have seen encapsulation at layer 2, where we add Ethernet header and Ethernet trailer. We have seen encapsulation at layer 3 when we add network layer header. And now you see encapsulation at layer 4 where we add layer 4 header. Layer 4 header is going to have 2 different types. It can be TCP header, it can be UDP header. Because some applications are working based on TCP, some applications are working based on UDP. At the end of the day, each of these applications is associated with what we know as a port number. This port is a logical concept, yeah? So don't confuse it with the physical port that you see on the devices. So these applications, being TCP-based applications, being UDP-based applications, they are going to be assigned to some port numbers. This port number concept is a transport layer concept, yeah? And this port number helps us deliver the data to the right application, because each application, as I said, is associated with a port number. So internet chat, this is associated with TCP port number 531. POP, Post Office Protocol, is associated with port 110. The web service running on that web server, for instance, is associated with port number 80 or 8080. Or if you want to contact that web server, not using HTTP, but instead using HTTPS, what is the port number that is associated to that HTTPS application? Anyone? Port number for HTTPS. A quick Google search.
What's the question?
443.
443. Good. So port number for associated to HTTPS server. So do I need to memorize those port numbers? Yes. For the well-known apps, you need to know them. When we do segmentation, as I said, it helps with efficiency of our transmission because we can't just send a large, big chunk of data in at one go. When we segment them, it also gives us the chance for multiplexing those segments. This is very important, guys, because multiplexing helps with a more efficient way of transmission in a sense that you can see that these segments towards the end of this figure, these segments, yeah, in all these shapes can be interleaved between each other, amongst each other, and they can be sent and received thanks to multiplexing and thanks to segmentation that happens at layer 4. In this way, everyone can use the medium, and chunks of data are going to be put in between each other, which is a more efficient way of communication rather than reserving the whole channel or the whole medium just for one party, one source and destination pair. Everyone can use it, and then transport layer is going to multiplex data for different applications. Remember, again, on that PC, as you can see, you are running a couple of applications. It's not just one application that you're running. As said earlier, port numbers are the way that we identify or distinguish one application from another. Port numbers are either TCP port numbers or UDP port numbers. TCP or UDP are the two de facto protocols at layer 4. You see some applications, therefore, are based on TCP. Some applications are based on UDP. And of course, few applications can use either TCP or UDP. The only application that you learn for this is DNS. So TFTP is a UDP-based application, whereas emails, SMTP, IMAP, POP3, all these three email protocols are TCP-based applications. File transfer protocol, FTP, has a sibling, and that sibling is TFTP, trivial file transfer protocol. One is TCP-based, another one is UDP-based. If you are after a reliable method for transferring your files, you go with FTP because you know that TCP is reliable. UDP, however, is not reliable in a sense that you are not requiring acknowledgement for the sent traffic. And therefore, if you want to send something fast, if you care about speed rather than reliability, you go with UDP. Yeah. And regardless of your transport layer application, you're going to encapsulate that segment or datagram depending on the protocol. The PDU at transport layer is either called segment or datagram. You know what PDU means, yeah? The form that data takes at each layer is called PDU. We are in transport layer context today, so the PDU is either called segment or datagram. If the protocol is TCP, the datagram is called segment. If the protocol is UDP at transport layer, the PDU is called datagram. So regardless of segment or datagram, i.e. regardless of TCP or IP, that PDU at transport layer is going to be encapsulated in IP at network layer, yeah? Meaning that you're going to add IP header, and then as you go towards the bottom from top, the IP packet itself is going to be encapsulated in Ethernet frame by adding Ethernet header as well as Ethernet trailer, and then you place the streams of zeros and ones on the medium. I like this word for describing TCP as being full featured. TCP is reliable once again because you are segmenting big chunk of data and then you are numbering those segments. That numbering helps you for in two different ways. When you number those segments, you can reassemble them easily at the destination side. This is for one thing. But also, with numbering those segments, you can track those segments in a sense that if the destination is expecting segment 1 through 10, but something goes wrong in communication from point A to point B, and segment 9, for instance, gets lost, source or sender does not need to resend the whole 10 segments again. Destination can just inform the source or sender that, hey, I have received segment 1 through 9, 1 to 9, but not 9, and 10. Therefore, can you only send me back segment 9, please? So you see this segmentation, this numbering can help the destination to specify the only missing or the only lost segment, and the sender will only resend that last segment. The rest have been already delivered, no need to resend them. So acknowledgement of what we have received or what is missing is something that TCP brings to the table, not UDP. With UDP, we don't have those mechanisms. Therefore, UDP is unreliable. So TCP being full-featured, for that, also TCP being full-featured in a sense that TCP can help you to determine the right rate at which you can send and receive segments. Yeah, this is known as flow control. UDP does not do any flow control mechanism, does not have any flow control mechanism. It's only TCP. Guys, things that I'm going through are pretty much the interview question, basic things around TCP and UDP. I'm not talking about advanced stuff, but for your level, you're going to get questions about TCP three-way handshake. You're going to get questions around TCP flow control, what we mean by that. So with flow control, for instance, the destination is going to tell the sender that you are speaking too slow or you are speaking too fast. Can you adjust your rate of sending segments? Once again, with flow control, destination is going to tell the source or sender about the appropriate rate at which the speaker must speak. Yeah? So destination is telling me that you are sending too many segments, which I can't digest. Can you speed down? Or the destination is telling me that, you know what, I have capacity, so why don't you send more segments? Therefore, you are going to adjust the rate at which the sender speaks. This is known as flow control, and this happens with TCP, not with UDP. TCP is also full-featured. I think I've mentioned that previously, in a sense that it does not allow for out-of-order delivery. In fact, it forces the destination to deliver the received segment in a timely fashion or in an orderly fashion, in a way that segment 1, 2, 3, 4 are all received first. If there is any missing segment, we're going to ask for resending it. And then once 1, 2, 3, 4, all segments of that conversation have been received, I'm going to put all together in order, 1, 2, 3, and then 4, and then deliver that to the destination. So sequencing and making sure that data is not delivered in wrong order to the application layer on destination side. We kind of looked as sellers who are going to sell TCP by telling you if TCP is good in this sense or in that sense or has in this feature or that feature. But how TCP does that? TCP, unlike UDP, is known to be a connection-oriented protocol. So When we are talking about UDP, we are saying that it's connection-less protocol. We are talking about, when we are talking about TCP, we are saying that it's a connection-oriented protocol. What do we mean by that? Connection-oriented, or connection in this context, relates to a session that is established before the actual transfer of data. Before the actual transfer of data. Remember, I'm sure you are making notes. So that session is going to be established through TCP between source and destination in advance. How do we establish this session? This session is going to be established through a mechanism called or known as three-way handshake. Basically, A and B, source and destination, are going to handshake, three-way handshake, we know it, and then this session is going to be established. This session is a temporary session, which is used by TCP to keep track of the actual data transfer. Things like which segments I have sent, things like can you acknowledge receipt of these segments, things like can you send back to me segment 9 because I have received everything else apart from segment 9, things like you're speaking too fast, can you slow it down? All those things happens over TCP temporary session, which is used